All right, so we have seen that you can use derivatives to determine when a function is increasing or decreasing. So the next step then is to find the location of local max and minimum points. Okay, so as it says here, the highest point is the point 7, 6. So we say that f has an absolute value, an absolute maximum, I should say, of 6, and that occurs at x equals 7. The lowest point of the graph is 0, 1, so f has an absolute minimum of 1. I said 0, 1, it's 10, 1. Absolute minimum value of 1 at 10. There are also relative max and min values of 2, 2, 4, 5, and 5, 3. So we can see all those points on that graph. So basically, what happens is whenever you have a max or min point, that's where the graph changes from either increasing to decreasing or decreasing to increasing. So we'll go through the same steps that we did yesterday, only we're going to add that extra piece. Where the graph changes from increasing to decreasing, that's going to be where you're going to have a local maximum point. And where the graph changes from decreasing to increasing, that's going to be where you have a local minimum point. And then we'll also see that in some cases, we're going to have absolute maximum or minimum values. So when we look at these graphs, the first one is the graph of y equals x squared. And as it says there, f at 0 equals 0 is the absolute and local minimum. There is no maximum value. But the graph of y equals x cubed has no max or min because it falls to the left and rises to the right. So there is no max or min value for that one. In the third example, this is the graph of y equals 1 minus x squared, but then notice there's a restriction on the domain. The domain is that x must be greater than or equal to 0, but only less than 1. And that's why there's an open dot at the point where x equals 1. So the scale for that graph is actually 0.25. Each vertical line is 1/4 of 1. But it's labeled as here where x is 1, so that is the point 1, 0. So in that case, as it says below, there is a maximum value at f at 0, which is 1, but there is no minimum value. As x approaches 1, y approaches 0, but it never actually gets there. That second graph, again, there's a restriction on the domain. It's the graph of x cubed minus 3x, where x is greater than or equal to negative root 3. So this point here is where x is negative root 3. And as it says for that graph, there is a local and absolute minimum, but there is no maximum value. So the point 1, negative 2 is a maximum, an absolute minimum, and at negative root 3, that would be a local minimum. It's the lowest point for a certain portion of the graph. But because the graph extends up to the right forever, it rises to the right, there is no maximum value. So these are the different scenarios that we're going to see. So again, all max and min values occur at points where the tangents are horizontal lines. Fermat's theorem states that if f at x has a max or min value at point C, then either f prime C equals 0 or f prime C does not exist. However, this does not always hold true. And one example is the graph of y equals x cubed. The first derivative is 3x squared, and the 0 of that is 0. But at x equals 0 for this graph, you get a point of inflection. Right? So not at every point where the first derivative equals 0 will you have a local max or minimum point. In some cases, you'll get a point of inflection there. But something is going to happen at that 0. Okay? And then the second example, that graph comes up to a point. It's not a curve. It comes up to a point. Now, we don't there is no equation for that graph, but sometimes you're going to be given a graph and not its equation, okay? And so for graph number 2, the point A comma f at A is a corner. It's not a max or min value. When it comes to a corner like that, the first derivative does not exist. F is not differentiable at A because it comes to a corner. So there is no equation for that graph, but if you see a graph like that, you have to know that in that case there is no max or min because it's not differentiable at that point, if you see one like that. So that's a special case. So Fermat's theorem does say that we should start by looking for the extreme values at the number C for which the first derivative equals 0 or where the first derivative does not exist. Again, we call these numbers critical numbers. So we want to find the critical numbers for the following. The first one, we are given an equation. That is a third degree polynomial. So we can differentiate it. So the first derivative is 3x squared plus 12x plus 9. And the critical numbers will occur where the first derivative equals 0 or where it's not defined. And in this case, there's nowhere where it's not defined. There are no restrictions on what x can or cannot be. Because there's no denominator, there's no radical. Those are normally the places that we see restrictions. So we solve the quadratic by factoring. And we get our critical numbers at -3 and -1. So there's our critical numbers, the zeros of the first derivative. Now the second one is f at x equals the absolute value of x. Well, there is no rule that we have to differentiate an absolute value function. It's not like you can write x to some power instead of using the absolute value symbols. It just doesn't exist. And once again, in this case here, this graph comes to a corner, okay? So in this case here, we say that y equals the absolute value of x is not differentiable at 0. Again, the graph is a corner. That point is a corner. So to find the absolute maximum values on a closed interval from A to B, we find the values of f at the critical numbers of f in the open interval from A to B. We also find the values of f at the endpoints, f at A, f at B. The largest of these values will be the absolute max, and the smallest will be the absolute min. So this will come when you have a closed interval. So instead of just be given an equation, you're going to be given an equation and a domain. So there's going to be restrictions on what x can or cannot be. So we'll start with that same equation that we did earlier. We found our critical numbers for this equation already. We factored it and got x plus 3, x plus 1 after taking out the common factor of 3. And that gave us critical numbers of -3 and -1. So we need to find the value of the function at f at -3.5 because that is the minimum value of this graph, at +1 because that's the maximum value of this graph, as well as at -3 and -1 because those are the two critical numbers. So to find out what these points are, you plug these values into the original equation. And at negative 3.5, the value is 1 1/8. At positive 1, the value is positive 18. At negative 3 in the original equation, the value is positive 2. And at negative 1, the value is negative 2. So you find the y value at the critical numbers as well as the endpoints of the interval. And then you compare them. The largest value is a maximum value. The smallest value is a minimum value. So there's our max and min values. And for this graph with those restrictions, those would be absolutes. Because of the restriction on the domain, the graph does not go on forever. It stops. It starts and it stops. So because the domain is restricted, in this case, we're going to have absolute max and mins. Right, number 2. We want to know the max and min values for that function between negative 2 and positive 4. So we start by finding the first derivative. Which would be 6x squared minus 12x minus 18. And the critical numbers come when that equals 0, common factor of 6. And then factoring the quadratic, that remains. Our critical numbers are at 3 and negative 1. So again, we need to find the value of the function at the endpoints, f at negative 2, f at 4, and also the two critical numbers, f at 3 and f at negative 1. So again, you would plug these values into the original function. They are points on the graph of the original function. So f at negative 2 works out to be negative 1. F at positive 4 works out to be negative 37. F at 3 is negative 51. And f at negative 1 is positive 13. So in this case, our absolute minimum occurs at f at 3, that's negative 51, and our absolute maximum occurs at negative 1, and that value is positive 13. Okay, for number 3, I would probably start by multiplying that out, and then we won't have to use the product rule to differentiate. So g at x would be 5x to the 2/3 plus, and when you multiply x to the 2/3 times x to the 1, that x to the 1 would be 3/3. So 2/3 plus 3/3 is 5/3. So now we'll differentiate. The 2/3 is multiplied by the 5 over 1. That'll become 10/3 x to the negative 1/3 plus 5/3 x to the positive 2/3. In each case, you're subtracting 3/3 from the exponents. That's the same thing as subtracting 1. Now we can simplify this a little bit by factoring. I'll take out a common factor of 5x to the negative 1/3. You see, if you look at the coefficients, both of those numerators are divisible by 5. And remember, when you're looking to take out a common factor of a power, you take out the power that has the smallest value, which is negative 1/3. Right? And so to get the other factor, a couple different ways you can look at it. You can divide each term by the common factor, or also ask yourself, what do we multiply the common factor by? And I'm looking specifically at the coefficients right now. What do you multiply 5 by to make it become 10/3? And the answer to that would be 2/3. And when you divide the x to the negative 1/3 out, they will cancel. Oh, I'm sorry. My common factor is 5/3. I apologize, not just 5. Because both of those coefficients have a denominator of 3. So this just becomes 2. When you divide 10/3 by 5/3, or ask yourself, what do you multiply 5/3 by to get 10/3? The answer is 2. And when you divide the x to the negative 1/3, they cancel. Plus, here the coefficients are the same, so essentially this coefficient will be 1. And then the power on x will be found by dividing these two x's. And you're dividing, you subtract the exponents. 2/3 take away negative 1/3 becomes 2/3 plus 1/3, which is 3/3 or 1. And so by factoring it, it makes it much easier to solve the equation. The first one will be where 5x, well actually let's also do this. Let's write the denominator, let's write it with a positive exponent on the x. So the x would move to the bottom with the 3, and it would become cube root of x, bracket 2 plus x equals 0. And so there is no 0 for the first factor, but there is a non-permissive value. And the non-permissive value here would be x can't equal 0, right? Because you can't have a denominator of 0. The cube root of 0 is 0, and that would give you a denominator of 0 on the bottom, because 0 times 3 still gives you 0. So our critical numbers occur where the derivative equals 0 or where it doesn't exist. So the first critical number will be at 0, because that is an NPV of the first factor. And then the second one will be when 2 plus x equals 0, which is where x equals negative 2. Yes? You can take the cube root of a negative number. The cube root of negative 8 is negative 2. Negative 2 times negative 2 times negative 2 is negative 8. Okay? So remember, the critical numbers occur where the first derivative equals 0, but also where it doesn't exist. And you see the original function doesn't have a restriction on x. Okay? Doesn't have a restriction on x. So x can equal 0 in the original function. It's just that with the first derivative, x can't equal 0. But you get your critical numbers from the first derivative, and then you apply it back into the original function. So we need to find out what g at negative 5 is, g at 1 is. Those are the two endpoints of our domain, as well as g at 0 and g at negative 2. So we need to check all these values out. So at negative 5, it works out to be 0. At positive 1, it works out to be positive 6. At 0, it also equals 0. And at negative 2, it's approximately 4.76. So if we compare all these points, the largest value is 6. That'll be an absolute max. And we have 2 places where it reaches the absolute minimum point of 0. 2 places where you're at the absolute minimum of 0 when you compare all 4 of those values. Okay? And for number 4, again, we start by differentiating. So p prime x will equal, when you multiply the 5 by the 2/5, the 5's cancel, and you'll get 2x to the 4th plus 3x cubed plus 1. Yes, 3x squared. Now, remember our critical points come from where the first derivative equals 0. And that means that the function changes from being positive to negative. But if we look at this function for the derivative, the power on the first x is to the power 4, the power on the second x in the second term is power 2. No matter whether x is positive or negative, when you raise it to the power 4, it's going to be a positive value. When you raise it to a positive 2, it's going to be a positive value. And then when you add 1 after all that is done, it's just going to make the answer bigger. The point is that no matter what number you put in for x here, the first derivative will always be positive, which means the original function is always increasing. So again, because all powers are even numbers, all exponents are even integers, p prime x is always going to be greater than 0. So therefore, p at x is always increasing. If you tried to factor that polynomial function, you would find that it's not factorable. There are no places where the first derivative will equal 0 because of what we just talked about. No matter whether x is positive or negative, that first term is always going to be positive. And then you're going to add another positive value. So it's just going to get bigger. And then you're going to add 1, so it's just going to get bigger again. It's never going to equal 0. So because all the exponents are even integers, the derivative is always greater than 0. So therefore, p at x is always increasing. So that means our critical numbers will only be at the endpoints of the graph. We're only going to have to find, in this case, p at -2 and p at 1, because those are the two endpoints that we're starting with. So p at -2 is -22.8. P at 1 is 2.4. So that first one will be an absolute minimum, and that one will be an absolute max. So you can work on those questions for practice. Everyone got that copy down? Okay, we'll go through the last exam.